We are now recording. Welcome to the electronics class for September 1. Before I start, let me remind you, type hello into the chat box so that you get credit for attending. And let me ask, does anybody have any questions about last night's homework? You guys agree it was pretty easy?
The questions were phrased strangely.
Phrased strangely. Okay, well, tell you what, let's go take a look at them. What I intend to do right now is actually go over the answers. All right, so here, hopefully you can see the questions now. So match each material with the category that best fits it. Okay, so that one I hope isn't too strange. All right, so bronze is a metal, therefore you should know it's a conductor. Graphite, yeah, you may or may not know about graphite because it's not really a metal. But if you did the reading, because I trust you did the reading, right? You should have known that it is a conductor. Fiberglass is an insulator. Any kind of glass is an insulator. Ceramic turns out to be an insulator. Water is a little bit tricky. If it's absolutely positively pure, it's an insulator. If you get a little bit of contaminant in it, it still is a pretty good insulator. But if you get a lot of contaminant in it, it's a conductor. The water that comes out of the tap has got a lot of contaminants in it. So it's a reasonable conductor. I mean, not as good as metal, obviously, but it's not bad. Glass is definitely an insulator, okay? And if you take almost any metal and get it super cold, near 0 Kelvin, which is also called absolute zero, so the metal at regular temperatures is a very good conductor. When you get it down super cold, it becomes a superconductor. All right. Next question, which of the following statements is false? Now here are some of the ones where I can understand that some of the wording might have been a little bit confusing. All right. All right, so the important one here is the one that's false, is the one that claims that traditional current flows in the same direction as the electrons. And this is something that I talked about last time, and the reading did a pretty good job describing it. Traditional current is what Benjamin Franklin defined things to be. So when Benjamin Franklin had some electric circuit, he took a battery and he hooked it up with a wire. He knew that something was flowing through the circuit. He didn't know what it was. He just arbitrarily guessed, and he figured, well, let's say that it's flowing from the plus side of the battery through the wire to the negative side of the battery. And so that's the way he defined things to be. Well, later, after he was dead and long dead, people found out that there is this thing called an electron, and it turns out that the current that's flowing is actually the electrons, and they're flowing the exact opposite of what Benjamin Franklin thought. So yeah, he had a 50-50 chance of getting it right, and of course he got it wrong. The rest of these, these are all statements that are true. Every single one of these is true. Okay, and now we have a bunch of statements, and you're supposed to identify the one that's true. Most of them are false. Well, the one that's true is this one. A semiconductor is a material that when it's absolutely positively totally pure, it's a really good insulator. And if you get any impurities at all, even just part per million level impurities, then it becomes a pretty good conductor. Now, some of you might say, well, wait a minute, just a few minutes ago, you said that water was like that, right? You said that water, when it's pure, is an insulator, and when it's got impurities in it, it's a conductor. So does that mean that water is a semiconductor? Well, not really, because in order for water to become a conductor, it needs more than just a few part per million. You need to have a lot of impurities in the water in order for it to be a conductor. Whereas with the semiconductor, if you just got 1 or 2 parts per million, then it can be a good conductor. So don't get that one confused. A lot of people do. Okay, so what is a Coulomb? Well, all of the statements here are true. A Coulomb is this many electrons. By the way, do you guys know about the scientific notation? So if I say 6.25 times 10 to the 18th, I wonder if you know that. Can everybody type into the box I want you to type in either yes or no. Yes means that you've used scientific notation before and you're familiar with it. No means that you've never seen it before. You have no idea what it's talking about. Okay, good. I'm seeing a lot of yeses. Now, if it's a no, be honest. And you can maybe you can send me a private message if you want. Okay, so I see one person had the courage to admit that the answer was no. So good for you for having the courage. All right. All right, so let me just really briefly talk about scientific notation. So if I've got some number that's 3.1 times 10 to the fifth, what that means is that's, I take that 3.1, oops, not 3.0, 3.1. Okay, I take that 3.1 and 10 to the fifth is a 1 with 5 zeros. So 10 to the fifth is the same as this. So what I'm doing is I'm taking this 3.1 and I'm multiplying it by 100,000. So basically I'm moving this decimal point over 1, 2, 3, 4, 5. So that means I have to add in 4 more zeros. So 3.1 times 10 to the fifth is the same thing. Whoops, boy, I just really messing up here today. Let's try this again. Okay. So 3.1 times 10 to the fifth is the same thing as 3100000. Okay. These two things right here mean the same thing. When you're dealing with really large numbers, which by the way is what we're going to be doing a lot of in this class, or really small numbers, okay, that applies as well. So this scientific notation comes in really handy. Okay, you just didn't know that was what it was called. Okay, good. All right, so glad to see that you're with that. All right, let's go back here to the quiz. All right, so a coulomb is one heck of a lot of electrons. So imagine a bucket with a whole bunch of electrons in it, 6.25 times 10 to the 18th. That bucket of electrons, okay, that would be what we call a coulomb. But also, a coulomb is defined as if you've got a current of 1 amp flowing. So when a current is a measure of how many coulombs per second are flowing through a wire. All right. So if you've got a current of 1 amp flowing through in 1 second, what that means is you've got 1 coulomb of electrons. Now, if you had 2 amps, then you would have 2 coulombs of electrons. All right, I see that somebody's playing with that. So I'm gonna, okay, so I've just disabled that, so you can't do that anymore. Okay. All right, let me come back here and clear that all. Okay. And it also turns out that a coulomb is a convenient way to measure electrical charge. Okay. All right. Now, this question right here, this is the one that gave most people the trouble. And I was very curious to see what you did with this one. If you did the reading, they talked a little bit about it, but even then they didn't really talk about it as well as they should have. This symbol right here, and which is the same as this one right here, okay? These are symbols that, that you apparently haven't seen before, and that's okay, don't worry about it. But there were a few of you that got this question right. So somebody who thinks they know what this symbol means, can you unmute yourself and tell us, what do you think this symbol means?
It's a ground symbol.
It's ground, okay. What does that mean in terms that a beginner could understand? What does ground mean?
It like, think. Oh, it says right there, it just allows current to flow through it.
Okay, well, here, let me explain it. Let me stop sharing here for a second here. Okay, let's suppose that I'm working on my car and I've got a light. I want to push a button on my dash panel and then a light comes on to the car. All right. Now there's a couple ways that I could wire this. One way is, so here's the button, here's the switch on my dash panel, and here is the battery for the car. So it's connected up to here. And then here is the light bulb. Okay, it comes back to here. All right. So when I close this switch here, so the switch is closed, electricity can flow through here and the light comes on. Okay, and this is something that all of you understand. But now if this light is really, really far away from my car, from the battery, let's say here's the battery way down here, and the light is way over here. And here's my switch. Okay, so let's say that one way I could do it is I could run a wire to there, and I could run another wire to here. So you see, I've got 2 wires that I have to run, which is not really that big of a deal, I'll admit. But maybe I don't want to do that, all that wiring. What I can do is I can kind of cheat a little bit. Let's say that this is the body of the car. This is the metal part of the car, okay, the chassis. All right. What I could do in order to maybe not have to use so much wire is I could take my battery and I could connect it up to the metal part of the chassis, and I could take my light and I could connect my light up to the metal part of the chassis. So I now don't need to run a wire from the battery to the, or I do need to run one wire. I mean, this wire right here, I have to run that. But the other wire, I don't have to run it, because when I close my switch and the electricity starts flowing through here, okay, it comes down here and it goes into this part, which is what we call ground. And because this is metal, that allows the electricity to flow through here and then back up in the battery. So it saves me, so I don't have to use as many wires. And if I have another light bulb over here, let me switch different color here. Okay. Let's suppose I have another light bulb over here. Okay. I can do the same trick with that. I can run a wire to there, and then again, this last wire, I can just run it back to that same ground. I don't have to run it all the way back to battery. All of the light bulbs that I have, I can have 6, 7, 8, 9. I can have as many light bulbs as I want. And the one side of the light bulb is all just connected to the chassis, which is metal. And so this chassis here is what we call ground. Okay, so I hope that makes sense. So on this question back here, hopefully you guys now understand that what ground is. So you'll understand that if it's connected up to, if the light bulb here is connected up to ground, ground is basically a chassis that's not necessarily shown in the diagram, and it doesn't need to be shown in the diagram. It's just understood that whenever you have this symbol right here, what it means is that it's connected up to some chassis. So you don't have to run that extra wire. All right. Yeah, Elliot, that'll be fine. Don't worry. See you later. Okay, any other questions about this particular? Go ahead.
So the thing that confuses me is like, it looks like that's like an earth ground, not like a chassis.
Ah, okay. All right, so you know that there's a difference between earth ground and chassis ground. Okay, this is good. So it sounds like you've got a little bit of experience with electronics. Yeah, that's a difference that I don't want to go into right now. Let's wait until later on in the semester, and we'll talk more about the difference between earth ground and chassis ground.
All right.
You are correct. There is a difference, but I don't want to go into it right now. People are just getting started. Okay, and was that it? Was that the last question? I think it was. Okay. All right, before I leave last night's homework and start talking about tonight's homework, are there any more questions? All righty. Okay, I'm going to go into tonight's assignment then. If my internet connection will allow me to. Boy, is it ever slow today. All right, so here's electronics. Do. All right, and let's go down to the assignments. All right. Tonight's assignment is this one, 1-3, voltage, current, and resistance. If you go into Canvas and click on this, it'll take you to a thing that looks like this, except yours will look slightly different. Let me click on preview. That way, then it'll look a little bit more on my screen like it does on yours. Okay. So first off, you see that I'm going to have you read 2 sections from our online electronics book. If you click on the link there, it takes you to a section from our online textbook, which eventually is going to come up here. Maybe. Wow, is my internet ever slow today? All right. Voltage and current. All right, so if you read through here, now I'm not going to read through this for you. It's not my job to read the text to you. It's your guys' job to read this for yourself, but I think it does a pretty good job of talking about what is voltage. You know, it does a good job of saying what is voltage, and then further on down, it talks about what is current. Okay, so understanding the concept of electric current. Okay. I'm going to give you a quick summary, but I want you guys to read this for yourself. Basically, voltage is it's like electrical pressure. You can see here in the drawing here, they've got an analogy. They're using water for electricity. They're saying that this symbol right here, which by the way, let me turn on annotation here. All right. This symbol right here is a shortcut for how to write a battery. All right, so I had a battery here a minute ago. Hang on, let me get one. Right, sorry about that. All right, so what we have here is a battery. And over here, I have a different battery. Can you see that? Okay. All right, so clearly this battery here is bigger, this battery here is smaller. So let's take a poll here. I am going to make a statement, and I want to know if you guys agree with the statement that I'm about to make. Okay, so I'm going to claim, now I'm not saying this is true or not, it's you to see. I'm going to make the claim that if I take this battery and hook it up to a light bulb, it's going to make the light bulb burn brighter than it will this battery, because this guy is big, right? Does it not make sense that a big battery might make the light burn brighter than a small battery? So I want you guys to tell me if you agree with that. Do you agree that the big battery is going to make the light burn more brightly than the small battery will? Okay, everybody needs to respond here. Most of you have, but there's still 4 of you who haven't responded yet. One more still needs to go. Okay. Well, I'm still, okay, there we go. Okay, good. All right, so this is really interesting.
Sorry,
Let me
it
share
froze
the
up.
results here with you. It's almost half and half. Almost half of you agreed that the big battery here would make the light burn brighter than the small battery would. Now, when I take these polls, I don't know who answered what. These polls are all they're all anonymous. If you are one of the people who disagreed, I'd like you to unmute yourself and tell me why do you disagree?
Because it supplies more current for a
Sorry,
longer
I
period of
forgot to
time.
put my headphones back on. Okay, so I didn't hear what you just said. Can you try to say that again?
The 1.5 volts just is just that it's able to hold more energy over a longer period of time. So
Ah, okay, very good. All right. So let me clear this up so it's easier for you. Okay, so Dallas is claiming the fact that this battery is bigger does not mean that it's going to make the light burn more brightly than the little one does. Dallas thinks that both of the batteries have the same voltage, whatever voltage means. Dallas thinks that they have the same voltage. He thinks that this battery just has more electron capacity. So Dallas is claiming that the big battery can make the light burn for a longer amount of time, but the light is going to burn equally brightly for both batteries because Dallas thinks that both of these batteries are what he said was 1.5 volts. Now, it turns out that Dallas is in fact right, okay? So voltage is not determined by how big the battery is. Voltage is determined by how tightly the electrons are squeezed together. So think of it kind of like water pressure. You can have a water that's or a pump, I say, a pump that squeezes the water, and some pumps really squeeze it really hard, and so the water comes out at really high pressure. Other pumps, they don't squeeze it quite so hard, so the water comes out at lower pressure. So think of it that way. Voltage is, you think of it as electrical pressure. And so in this case, the pressure, the electrical pressure, is not determined by the size of the battery. The electrical pressure is determined by what type of chemicals are inside the battery. And Dallas is correct in recognizing that we've got the exact same chemicals in this battery as we do in this. They are the same chemicals. We have more of them here, but they are the same chemicals, and therefore the voltage or the electrical pressure is going to be the same in both of these. All right, so remember, voltage is like electrical pressure. All right, and a good way to think about electricity is compare it to water. So what we have here, let me turn on annotation. What we have here is a pump. So it takes the water and it brings it in the pump and it pressurizes it and it causes it to flow up here. And so if it was a high pressure water pump, it could go way up here. If it's a low pressure pump, it can only go here. So the height that we're able to pump the water is determined by how much pressure the pump can put out, just like a battery. All right, so I think we got voltage nailed down pretty well. Let's talk about current. So what is electrical current? Well, it turns out that if you use the water analogy, it works pretty well, the same thing. So let's suppose that let me turn on my annotation. Let's suppose that I look at this point right here. So I draw a line right here, and I watch this line to see how many drops of water per second go past that point, right? what I could do is I could count how many drops of water per second go by there. That would be a way of measuring the water current. Now, counting the drops per second is going to be a little bit hard to do, so maybe it's better if I use a different unit. How about let's count how many gallons per second go by. That might be a more convenient way to use it. But either way, whether I count drops per second or whether I count gallons per second, in both cases, what I'm doing is I'm finding out how much water per second is flowing by. That is the current. Well, electricity works exactly the same way. What I can do for water, I can also do for electricity. All right. What I can do is I can pick some point right here, and I could, in theory, count how many electrons per second are flowing through there. But that's going to be kind of hard to count that. So what I need is kind of like a bucket of electrons. Well, that's where the Coulomb comes in. A Coulomb of electrons is kind of like a gallon of water, okay? It's a more convenient unit to use. Rather than having to count electrons per second, what I'm going to do is I'm going to define this unit that's kind of like a gallon of electrons, so I'm going to call it a Coulomb, and I'm going to count how many coulombs per second go past here. So you see electrical current and water current, very, very similar, right? So it's a measure of how much is passing by a certain point. All right. Now there's one other quantity that we need to understand, and that is the quantity of resistance. So if we go back to our assignment here, if we click on this link right here, it'll take us to the same place that we get if we click on down here. It'll take us to the next chapter in our online textbook, which is talking about resistance. Now, resistance in electricity is kind of like resistance of water flowing through a pipe. All right, what you see right here, let me turn on annotation again. Okay, so we have electricity flowing through a wire, and something in our path here is causing it to slow. Well, it's pushing back. I was going to say it's causing it to slow down, but I don't want to use those words. It's pushing back. So we've got this high pressure battery pushing the electrons through here, and here we've got a lamp that's pushing back. Now, if it's a little tiny lamp, it can't push back very much, so we say it doesn't have very much resistance. So we can get a lot of electricity flowing through here. If the resistance is small, I can get a lot of electricity flowing through there, or in other words, we would say the current is high, right? But maybe I get a bigger, stronger electric lamp, and it's able to push back harder. So in that case, I'm still going to get a little bit of electricity flowing through it, but not as much. All right. So I need you guys to type into the chat box whether, is this making sense to you, or do you want a little bit more explanation? So if this makes sense to you, I want you to type in yes. If you need a little bit more explanation, I want you to type in no. Okay, I'm seeing a lot of yeses. If it's a no, be honest, that's okay. All right. All right, so I'm seeing basically all yeses. All right, good. Okay, so now let's go back to our Canvas account, and we're going to do some experiments now. If you guys were live in my room here and we were face to face, then we would actually get out some real batteries, some real light bulbs, and some real wires, and we would hook them up. But unfortunately, that's not an option here. We're doing this online thing. And so we're going to go to the class resources, and we're going to look at this thing, the Online Circuit Experimenter. This is something that we looked at before. It's a software simulator, and we're going to be using this a lot. Now you see we have two options. We have intro and we have lab. if we click on intro, we get this. And down at the bottom here, if we can go to lab, and you'll see there's not much difference, intro and lab. The only thing that's different is with the lab, you have an extra thing over on the right here. This tool right here, if we're in the lab, we have it. Whereas if we're in the intro, you'll see we don't have it. Other than that, intro and lab are basically the same. Well, also there's this guy and this guy that we have in the lab that we don't have in the intro. Okay, so you see they're not there in the lab, but they are there in the intro. But they're not really that important for us. Okay, so I want you guys to be into the lab because this tool right here is an important tool. So when you click on the link here, make sure you go into the lab, not the intro. All right, now in your homework tonight, in addition to asking you a bunch of questions, I'm also going to give you an assignment where I want you to make some circuits using our online simulator. So we're going to start with the battery. And if you click on the battery, you'll see that it brings up this, this slider down here. We can change the voltage of this battery. Now, some of you are going to say, well, I can tell by looking at it, that's a AA battery. And some of you know that a AA battery always has 1.5 volts. But in our simulator here, this actually is not necessarily 1.5 battery. We can take this guy all the way from 0 up to 120 volts if we want, and we can have it be anything in between. All right, so let's just set it for some intermediate voltage right now. All right, and the next thing we're going to do is we're going to take a wire, and we can make this guy long or short if we want. And then I'm going to take a light bulb, and I'm going to make it like this so that the two circles are directly above each other like that. Oops, come on. Okay, so I've hooked up the light bulb there. And now I could just connect the wire directly up here. All right, so as soon as I connect it up, electricity is flowing. Right now, over here on the right side, you guys might not be able to see on the right side because you might see all of the video things on the right. Let me. Okay. So over here on the right side, this thing that I'm pointing to here, if you can't see it, then please move that little window so that you can. You can see that I've got a couple options here. So one of my options is show current, and I can do it either as electrons flowing or I can do it as conventional current. So we talked about this in last night's homework. Remember, conventional current is what Benjamin Franklin came up with. So he looked at the plus side of the battery, he looked at the minus side of the battery. He saw that the light was on, so he knew that something was happening, but he didn't know what direction it was flowing. So he arbitrarily said, well, I'm going to treat it as if the electricity is flowing from plus to minus. And then after he died, people found out that actually that's not what's happening. What's actually happening is that it's electrons that are flowing, and they are flowing in the opposite direction. But by the time that people figured that out, all of the textbooks had already been written, and people didn't want to have to rewrite the textbooks. So we still talk about electricity flowing as if it's flowing from the positive side of the battery to the minus side of the battery. And I apologize if that's confusing, but that's just the way it is. Not much we can do about that. All right. So remember how I said that if I click on the battery, I can change the voltage to whatever I want. Wow, look what happens when I turn the voltage up. That light gets really bright. Turn it down, not so much, and then all the way to 0, okay? All right, so I can adjust the voltage of the battery. Well, it turns out I can also adjust the resistance of the light bulb. If I click on the light bulb, then down here at the bottom, I get this nifty thing. So I can have the resistance go anywhere from 0, which, by the way, you see what happens when I go to 0 resistance? I burn out my battery. The current is so high that my battery just burns all the way out. Okay, so I go to some non-zero resistance, and the higher I go, the dimmer it gets. So if I take it all the way up to here, so my maximum amount of resistance is 120 whatever units we use for resistance, which turns out to be ohms. Okay, so the light bulb's not as bright. Okay, now, what if I play with the voltage? So I'm going to pick some intermediate. I'm going to pick some intermediate value for my resistance here. How about 50? Right? So my resistance here is 50 ohms. Well, what about my battery? You see what happens when I turn up the voltage on my battery? The light bulb gets brighter. Turn it down, it goes to 0. Okay. Now, I want to know how much current is flowing through my circuit. That's where these tools over on the right come in. If I click on this guy right here, this is a current meter. And if I take this end right here, see how I can move it around? If I position this on the wire, bingo, it tells me how much current is flowing. Now, if I click on the battery and increase the voltage, you see what happens? The light bulb gets brighter, but also the current goes up. So it goes to 2.2. So if I take it all the way up, my current here is at 2.4 A's. By the way, what does an A stand for? What units do we use when we're measuring current?
Is it amp?
Amps.
Amp. Amp is exactly right. Okay, now the official term is ampere. So what we really have here is 2.4 amperes, but almost nobody calls it an ampere. Everybody just abbreviates it to an amp. All right, so when our voltage is 120 and our resistance is 50, then our current is 240. Now, I'm getting kind of tired of having to click on these things to find out what the values are. So if only there was some way that I could get the software to display the value of the battery and the value of the resistor without me having to click on it. Gee, that would be so nice. Have any of you guys played with this enough yet to know that it's possible to do that? All right, apparently not. Look over on the right here. Let me turn on the annotation. All right, look over on the right here. You see this box here that says values? Well, that's what I'm going to do. I'm going to click on values. And hey, look at that. Now the numbers all of a sudden appear. So that's kind of nice. So now if I click on the battery, okay, I can adjust the battery, but I don't need to look down here because it tells me on here. So you see here, I changed the voltage on the battery. The light bulb gets bigger, gets brighter or not. Notice the resistance value. The resistance does not change. It's always going to be 50 ohms. Doesn't matter what the voltage is. The resistance is always 50 ohms, but the current, that definitely changes, right? If we look at the current here, okay, look what happens when I change the voltage. So if I raise the voltage, see how the current went up all the way? So it's up at 2.21 now. If I drop the voltage, the current goes down to 0.73, or if I drop it all the way, it goes to 0. But notice even at 0, the resistance of that light bulb there is still 50 ohms. And by the way, that upside down horseshoe symbol, okay, this symbol right here, the upside down horseshoe. Anybody know what that is? What that's a Greek letter. Anybody know what Greek letter that is?
Omega.
It's the omega, the final alpha letter.
Very good. Yes, it's omega. And omega comes in two flavors. There's capital omega and lowercase omega. So in your math class, you may have seen that little W sign, and your math teacher may have called that omega. Well, your math teacher's not lying. It's just that this one here is capital omega. This one here is lowercase omega. All right. Okay, so in your homework tonight, I'm going to ask you to build various circuits, and And like, so what I might do is I might give you some mystery light bulb where I make it so that the value of the light bulb is hidden. Okay. So let's say I've got that thing totally blacked out. So well, not very well blacked out. Pretend that that's completely blacked out, right? Maybe if I do this, does that black it out? It's still not blacking it out. Okay, well, you're just gonna have to pretend that that thing's blacked out, right? And so what I might do is I might say, I want you to adjust the voltage so that we get a current of, let's say, 0.5 amps, okay? All right, so let's say that the desired current, okay, so desired current is 0.5 amps, all right? So your job is to find out what value of the resistor is going to do that for me, or I'm sorry, what value of the voltage is going to do that for me. Well, pretty easy to do. Just turn the voltage up until you get it to where you want it. Okay, I overshot it a little bit. There we go. Okay, so it turns out that if we want to get 0.5 amps of current, the voltage that we need is 25. Okay, now next time we meet, we're going to be learning a mathematical formula that allows you to calculate this ahead of time. And in fact, I'm willing to bet that at least half of you already know what that formula is. Okay. Anybody want to speak up with what the name of that formula is? Come on, I know some of you know it. What is the name of the formula that we could use that would tell us what is the current?
Ohm's law, right?
Ohm's law, that's exactly what I'm looking for, yes. All right, so next time we meet, we're going to talk about Ohm's law. But for tonight's homework, we're going to pretend that we don't know Ohm's law. Now, a lot of you, you're not going to need to pretend because a lot of you don't know Ohm's law. But those of you that do, when you do tonight's homework, if you want to use Ohm's law to solve the problem that way, I'm okay with it. But I would actually hope that you would do this just experimentally here. So let's just go in here and just say, okay, I don't know Ohm's law, so what I'm going to do is I'm just going to play with the voltage until I get the current that I want. Or maybe it won't be the voltage we play with. Maybe what it'll be is it'll be the resistance that we play with, okay? And maybe we won't have just one light bulb. Maybe we'll have two light bulbs. So if I want you to have two light bulbs, you guys hopefully know that if I click on these little joints here, and then it gives me a little scissors so I break it, okay? So then what I can do now is I can bring in another light bulb and put it right here. Okay, and then let's bring in a wire and connect that up. And then there we go. Okay, so now we have two light bulbs. So if I measure the current, okay, I find that it's 0.75 amps. What if I were to measure the current somewhere else? So tell you what I'm going to do. Let me ask you guys a question. What if I were to take my current meter and instead of measuring it here, what if I hook it up to measure right here? I want you guys to type into the chat box, what number do you think I'll get? So if I'm getting 0.75 amps flowing through the lower half of the circuit there, if I were then to take my current meter and stick it up and measure the upper one, anybody want to make a prediction for what number I would get? All right, I'm seeing 0.75 with a question mark. Okay. And I'm seeing 0.5 without a question mark. How about somebody type in 0.75 with an exclamation mark, okay? Can somebody do that for me, make me happy? Oh, thank you. Thank you, Luke. Okay. Yes, the answer is 0.75 with an exclamation mark, okay? And just in case you don't believe me, let's go see. Okay, so down at the lower hand, we have 0.75. Now we go up, yep, sure enough. And it turns out it doesn't matter where we measure the current here. If we've only got one loop, if we've only got one branch in our circuit, I can measure it anywhere I want. It's going to be 0.75, okay? Now, if I wanted to, I could get fancy here. I could maybe have multiple loops in my circuit. How about, I know what we could do. Tell you what, let's do this. All right. Let's say we got one branch that looks like that. And I've got another branch that say looks like this. And okay, so I'm going to bring in a wire here. Okay, so now you see I've got two loops in my circuit. So now, if I put my current measure here, I get 3.25 or 3.2. If I put it over here, I get a different number. And put it up here, I get still a different number. See, so I've now made it a lot more complicated. Let me turn this on. Okay, so I've got one loop that goes like this, and I've got another loop that, let me do it in a different color. I've got another loop that comes like this, okay? And so now I do not get the same answer. If I put the meter here, I get 3.2, I put it here, I get 0.98, I put it here, I get 4.8. Okay, so I've got multiple branches in my circuit now. Now for tonight's homework, okay, for tonight's homework, I am not going to give you a complicated circuit like that that has multiple branches. For tonight's homework, it's going to be simple. You're just going to have one branch. But don't worry, we will learn how to handle circuits that have multiple branches. We will do that pretty soon. We'll do that maybe next week, depending on how things go. But for tonight, we'll keep it simple, just one branch in the circuit. All right. So I think that you are now pretty well positioned. You should be able to do the homework tonight without too much trouble. The first couple of things in the homework are just questions. So if you read the assignment, you should be able to know the answers to the questions pretty well. And then the second part of the assignment is going to be, you're going to have to create a circuit, kind of like we're doing here. And so make sure that you know how to use the software. I think this software is pretty easy to use. Now you can play around with different things here. You guys hopefully know that you can put in things like the switch here. All right, so see how I connect it up? Nothing happens because the switch is in what we call the open position. And now when I close the switch, now electricity flows. Click on it again, switch is open, click on it again, the switch is closed. Now, some people get a little confused because they think of a switch like being a door. With a door, if the door is closed, can things go through the switch? Can go through the door? No, they cannot. But with the switch, it's the opposite. When the switch is closed, that's when the electricity can flow. And when the switch is open, that's when it cannot. So be careful. Don't think of a switch and a door as the same way. Okay, that can get people confused. All right. So I highly encourage you guys to play with this circuit simulator. Tell you what, hey, there's one more thing we haven't played with yet. This guy right here, this voltage meter. Let's play with that. Okay, let's close our switch. So voltage, remember, is pressure. All right. So if we want to know what the electrical pressure is, we can put one of these guys at one end of the battery, put the other guy over here at the other end of the battery, and you see it's now telling us what the voltage is. And if we click on the battery, it better agree. If the number on the voltage meter doesn't agree with the number on the battery, something's seriously wrong. Okay. And then what if I put the thing down here? Now I'm getting 0 voltage. Interesting. So anywhere up here, so if I put it on the battery or anywhere on the wire up here, you'll notice I get 9 volts no matter where I am. As soon as I cross over the battery, now it goes down to 0, so I get 0 volts. So remember, this is pressure relative to the black lead. The black lead is what we're going to call the ground lead. The black lead is always defined as the 0 pressure point. So if this wire is directly connected to the 0 point, then the wire has no resistance, and therefore the voltage is going to be that way. So tell you what, let's make this a little more interesting. Let's put in 2 light bulbs. Okay, now let's measure our voltages. All right, so we measure the battery. We see we still got 9 volts. Anywhere along here, we got 9 volts. When we measure at this wire here, oh, hey, look at that. The voltage went down. The pressure went down. And by the way, let me switch back to the conventional current. I want you guys to get used to using conventional current, not the electron flow. But you'll notice it didn't change the voltage. All right, so we've got all of the electrons in this part of the wire are packed together really tightly. So they have 9 volts of pressure. Think of it as pressure. Now, pressure isn't really the official word that we use for it, but it's what I like to use because it makes it easy to think of it that way. So we have high pressure on this side of the light bulb. We come over to the intermediate here, and we have lower pressure. Come over to the other one, and now we have 0 pressure. All right, so I want you guys to play with these tools. An important part of the homework tonight, not just answering the questions in the homework, but playing with the simulator. Build me a bunch of different circuits. Build some simple ones. Build some complicated ones. Play with it. You learn a tremendous amount by playing with it. Now, if we were in person at the Ames building, I would give you real voltage meters. So, by the way, this is a real voltage meter. Okay, and it's got these little leads that look very much like the leads that you saw before. Let me put a white paper behind it so it's easy. Okay, it's easier to see now. Okay, so these are the leads that you use to touch things. So they're identical to what you saw in the little simulator. Therefore, if I wanted to measure the voltage of this battery, what I would do is I would take the black lead and I would touch it to the negative side of the battery, take the red lead and touch it to the positive side of the battery, and I'd look on my meter and it would tell me what the voltage is. Okay. Measuring current is a little bit more tricky. We'll talk more about that later. All right, I'm thinking this is probably a good stopping point for today. Before I end the meeting, 2 things we got to do. One is I want to ask if there's any questions, and the other is I want you guys, before you leave the meeting, make sure you type bye, because otherwise you don't get credit for attending for the whole meeting. So if you don't have any questions, you can just go ahead and type bye, and I'll see you on Wednesday. If you do have a question, hang on, I'm going to turn off the recording feature because some of you may be reluctant to ask questions because you know you're being recorded and you don't want to be embarrassed. Let me turn off the recording feature.